Okay, what kind of questions do you have from the readings? No questions, no reading. You don't have to know any of that sulfate. So what we finished up when we talked about yesterday, making the sulfates, just making sulfates or nitrates or phosphates, you don't have to know any of those mechanisms. And those are mostly, I think, those are not reactions that we do. So if you're doing, there was reactions to take an alcohol and create the sulfate out of it, which would be like that, or you could form the phosphate, same thing. And then the phosphate, sulfate, and what's the third one? Nitrate. So when you form the nitrate out of it, you can form all of those. Those are esters. So sulfate ester, phosphate ester, nitrate ester. I think the phosphate esters are what you learn about in biochemistry. To basically, that's what holds the base pairs in a DNA. Is the phosphate. The sulfate. There's a lot of sulfate molecules, but you probably won't deal with those. And nitrates, the nitrate esters they're used more industrially. So the nitrate, the problem with the nitrate esters is that they're a little flammable, a little explosive. So for instance, the nitrate ester, I know if you go on YouTube and you want to see like a nitrate ester, if you take a piece of cotton that has lots of sugar, starch in it, and it's got lots of OH groups off of the six-membered ring, something that looks like this, although it'd be CH2OH group here. If you take that cotton ball and you stick it in a mixture of nitric and sulfuric acids, you can actually nitrate the OH groups, and then if you carefully dry it, then if you take it and put a match to it, it just goes up in a huge ball of flame. That's pretty spectacular. Those were the basis. That's, if you've ever heard about old films, they have to put old films in an anti-flammable basement somewhere in Hollywood because those are all made of nitrates, and so they have a tendency to catch on fire. So all the old films have to be very carefully stored. And the nitrate is what Alfred Nobel ultimately made dynamite out of, was using nitrates. And then Alfred Nobel some of his family members got blown up while making the dynamite products. So at the end of his life, he gave the money to the Nobel Foundation, and that's why he gives the Peace Prize in medicine and chemistry and physics and all of that, because basically it was a family business. I think he's like the sixth cousin, 5 times removed from like one of my great grandfathers. But if you have any kind of Swedish heritage, you would probably be related to Alfred Nobel. There was no money involved. But so those, they have practical, but I think if you go back older exams, you're never going to see a question about that. But you will, when you talk about biochemistry, you will talk about phosphate esters. What else? Let's go back to yesterday then, and wrap that up. So, could you tell me the reagents that you would need to perform each one of these transformations? So we want to form the least substituted and the most substituted double bonds. So how would we do that? So I'll give you a few minutes to Can you do it in one step? Maybe. If you can't, then you need multiple steps. And actually, let's do this. Let's use that for one or two, but you can't use it for the other. So you should be able to do one of these with one reagent, one step, but then do the other one once. So then the other one you're going to have to do it in multiple steps, just like we looked at yesterday. How you had to convert the OH to something else. You may have to convert the OH to something else and then do your reaction.
So like, how we do this yesterday.
Yes. Yes. So how do you convert? So you have to convert the OH to something else to make one of the products. But I don't know about that. You got to form these. You got to form the product.
Do you have to specify which one of these you use?
No,
Like
there's no
for
stereo. There's no stereochemistry, so you don't have to.
Is this right, or do you have to do, or is one?
So you could do this one in one step without making it fly.
Okay, so it looks like people. Okay, so how do we take the alcohol? How do we take the alcohol directly to a double bond? What reagent do we use? I know you have it written down. Somebody answer me, or else here we'll just do this. HCl and heat, no. I want to make the double bond. I need the heat, yes. But HCl would what would HCl do? HCl would protonate the OH, sulfuric acid and heat. So if I want to do this, H2SO4 and heat, that's going to always give me the most substituted product. So I could do that one in one step. It's the other one. So what do we have to do with the OH? Convert it to a Cl. So I need to convert that to a chloride and then react the chloride with tertiary butoxide in order to remove the hydrogen, the beta hydrogen that's least sterically hindered. So how do I convert the OH to a Cl? You'd use what? SOCl2 or HCl would work in this case because there's no possibility of rearrangements, or no?
Well,
Ask.
Could you have also used like a
You could have used a tosylate. I didn't see anybody use the tosylate. The thing is, we have multiple ways of doing this. They both would work. So if you wanted to, you could take, let's see, what's the last chloride? Like PCl3 or PCl5 would be. So any of those would work, as would taking the OH, reacting it with the tosylate, with the tosyl chloride, which has a benzene ring with the CH3 on it. And then that would make the tosylate ester. And then you could react the tosylate ester with your tertiary butoxide and still make and remove the least substituted beta hydrogen. So would there be an advantage of one over the other? Maybe experimentally, but on paper they would be identically the same. So you could either make the chloride or the tosylate ester. I mean, I'm going to probably ask you to make both on paper. If I could ask you if I wanted you to make the chloride, turn a chiral alcohol into either retention, inversion, or 50-50, I could ask you those reagents. And I would probably guarantee that that is something. So we have to go back and remember that the SOCl2 does what? In this case, it doesn't, because there's no chiral center. So the question was, could I in the future? And the answer is yes. So I could do exactly what I did yesterday, which is to say, okay, here is a chiral alcohol, same one we had yesterday. I want to turn that into, I want to retain the configuration on the chlorine, or I want to invert the configuration of the carbon with the chlorine, or I just want to make a 50-50 mixture of R and S. And so would I ask you to provide those reagents, or could I provide those reagents and ask you the products? Yes. And so we would have to fill those in. So retention would be, SOCl2 would be retention, 50-50 would be HCl, and inversion would be 2 steps. Use a tosyl chloride first, and then a Cl minus to do. So first step tosyl chloride, second step Cl minus. Overall, that is an SN2. That's what will lead to the inversion. Yeah.
Would the chloride perform tosyl chloride when it responds to would that react?
It could do that. Yeah, so whether you need the second chloride or not, but this just makes it easier, because the other thing that's going to happen is that if I'm not running this reaction in water, this Cl is going to combine with the H plus from the alcohol and make HCl. Now, if it's in water, that HCl is going to dissolve in the water and be completely dissociated. But if this reaction is not in water, when the HCl combines together, it's going to form the gas. And when you generate HCl like that in a reaction, you can kind of see the smoke coming out of the container, because that's the HCl gas being formed. There's nothing for it to dissolve in, and so it just comes out. So it would really depend on the solvent, and I think in this case, this tosyl chloride is not compatible with water, because the water would come in and replace the chloride, and you would end up not having a tosyl chloride anymore. So you couldn't do this in water. But if it was in a solvent where the chloride wasn't attached to the H+, it could go back around, but it won't. So I could ask you for the reagents or to write the products, something like that with the stereochemistry. And probably after we've done it twice, I think we're getting closer to being guaranteed that that'll be something on next Monday. Hannah? So will you use H2SO4 when you have the alcohol? So for instance, if I had this alcohol and I said, I'm going to react this with H2SO4 and heat, this reaction is going to be the dehydration reaction. So it's going to eliminate water to form the double bond. H2SO4 and heat always basically produces the most stable. Well, let me take that back. What we should do is we should go back to basics here. What's the major product of this reaction? I'll label. You've got an A, a B, and a C. So where should the double bond go for this reaction? Between A and B or B and C? A, B? Do we all agree with that? So whenever you're going to do the dehydration, if we take the step back and say, okay, here's my alpha carbon, here's my beta carbon, here's my beta carbon. So we should always do that and say, okay, which products could be formed? And as long as there is a beta hydrogen, you're going to be able to form that double bond. So if you can form more than one double bond, you're always going to form the most substituted double bond. So we're going to form that product as our major product, and that's going to be the Zaitsev product. Now, the reason I'm not saying that you would necessarily only get the Zaitsev product is because, let's say you had that alcohol and you're going to do H2SO4 and heat on it. Well, here's my alpha carbon, and then how many beta carbons do I have? I have just one. So if you have a primary system that only has one beta carbon, you're only going to form one product. So you have to take a step back. If there's more than one possible product formed, H2SO4 is always going to form the most stable product. But if there's only one possible product, that's the product you're going to get, period. So that's what H2SO4 does. H2SO4 with the alcohol will give you the most substituted one. If you want the least substituted one, you've got to change the OH to a chloride and then use tertiary butoxide. Or change the OH to a tosylate and then use the tertiary butoxide. Because the tertiary butoxide will not eliminate the alcohol. And that's where we were at yesterday. So if you want the least substitute, if you have an alcohol and you want the least substituted product. Like if I start with the alcohol I have here. So if I have this alcohol and I want to form the least substituted double bond, I need to first convert the OH to like a chloride. And then I can use tertiary butoxide to do elimination, because that base will then deprotonate the least substituted. And I'll form basically the Hoffman product. But tertiary butoxide will not eliminate an alcohol. So you've got to change the alcohol to the chloride by using something like SOCl2 or BCl3, or in this case HCl would work. And if you turn it into a chloride and then use NH2 minus, you're going to get the most substituted product as well. But you can get the most substituted product in one step. So that's what we did yesterday. So does that kind of make sense? Any questions still? I don't think anybody's going to ask any questions. So that was the reactions of alcohols, and basically turning an alcohol into a halide or turning the alcohol into a double bond. So then the next functional, and then oxidizing it, making the alcohols from the Grignards, that was all of chapter 14. So now for chapter 15, we want to talk about making ethers. And we already know how to convert a double bond to a cyclic ether, the epoxide, by using what reagent? To use a peroxy acid, which means it's got an extra oxygen in the carboxylic acid. So peroxy acid will do that in one step. And then once we make the epoxides, we can open them up under acidic or with a strong nucleophile. Okay, and that's sort of reviewed here in chapter 15. So we'll come back to that if necessary, but that's what you did yesterday. Now, what other ways do we know how to make ethers? Because whenever we talk about making ethers, the first thing that the book does, and this is what I would do, is I would go back and I would basically review how many ways do we know how to make ethers. Well, that's questionable, right? Because we could say, I can convert that double bond into that ether. And what reagent would I use? Anybody have? Do we like that? I'm not erasing it, so it must be good. So what I was going to suggest was, what did I add to the double bond? I added an H and an OCH3. What is this reaction similar to? It's similar to adding H plus H2O, right? So I don't know how many times I said it a lot. If you can do something with water, you can do it with alcohol. It's the difference between HOH, which is H2O, and HOR. So we could replace our water in all the alkene reactions that we learned. We could replace water with an alcohol and make an ether. And so this is just one of those examples. Replace with methanol water and you would make the ether. I could do the same thing in this reaction. Now let me put two methyl groups here and say, okay, I'm going to add an H and an OCH3 group to that double bond. So I've added an H and an OCH3 group, 100% trans. So what reagent would I use for this? You want a hint? It's not going to be a tremendous hint, but in order to add the H and the OCH3 100% trans, what kind of intermediate did I need? I needed a triangle. So what reagents go through a triangle? Greg? Anything with a BR? Well, since you mentioned the BR, I could use BR2 and methanol replacing water to make not a bromohydrin, but the ether derivative of a bromohydrin. So that's possible. And the BR and the OCH3 would add 100% trans. It would add Markovnikov if I didn't use two methyl groups. So what reagent that goes through a triangular intermediate do I use to add H and OH? The mercury acetate. And normally that would be mercury acetate and water. But now I'm going to replace the water with the alcohol. And then what do I add at the end? BH4. So if you go back through your chart of alkene reactions, every place we added H and OH, or added a BR and an OH, whenever we added a water, we can now add an alcohol. We can now add an alcohol if we want to make an ether. Okay. So this is kind of review. This is the way we can take all those reactions, replace them, replace water with alcohol, and now we make an ether. So there's no new reactions here. And actually there really won't be any new reactions as we make ethers, because I'm going to use twists of SN1, SN2, and acid-base reactions. So as far as reactions we already know, this is how we would do it. Replace water with alcohol. We get those products. Now, let's talk about a new reaction that's not really new. There's a reaction called the Williamson ether synthesis. And to do Williamson ether synthesis, what I need to do is take an alcohol and I need to convert it to an alkoxide. And then once I have the alkoxide, I'm going to react it with an alkyl halide so that the alkoxide will come in and kick off the halogen so that I now can form an ether. With this second step being what kind of mechanism? This reaction right here is what kind of reaction? It's going to be SN2. So the issue is, okay, I can do that reaction, it's just an SN2 reaction, but how do I make the alkoxide? Give me a reagent. You could use NaH. So NaH is what? It's sodium hydride, but what's the important part? It's not the sodium. It's the hydride. Hydride is the second strong, well, it's tied for the first strongest base we can have. So if you use hydride, I'm just going to do a deprotonation reaction. So I'm going to deprotonate the alcohol with H-. We should probably look at the periodic table and think about, in terms of basicity, what our strongest bases are. So in terms of our bases, what's going to be the strongest base that we can have? What minus? A C- is the strongest base that we can have, and it turns out that an H- is going to be comparable. Then what? What's the next strongest base? N minus. Our favorite N minus base is NH2 minus. Then what would be next? Next would be an OR minus, but what am I trying to make? OR minus, right? So on the periodic table then, basicity increases as you go from right to left. If I'm trying to make an O minus, I've got to either use an N minus, a C minus, and now I'm going to throw in an H minus. So you might say, but wait, we had another source of H minus. What was our other source of H minus? NABH4 is also a source of H minus. It turns out that NABH4 doesn't necessarily deprotonate alcohols all that well. Lithium aluminum hydride will, but sodium borohydride not as much. So that's why we usually go to a pure H minus, like using sodium hydride, or you might even see potassium hydride as the source of hydride for this. There's issues with those, but they both would work. Okay. Potassium, much more reactive. Of the hydrides, those are the only two that you could probably use safely. Because if you go down the first row, could you get cesium hydride? I don't know. Because if you go down and we'll come back, when the first row is going to be important here. As you go down, potassium's more reactive than sodium, more reactive than lithium. There isn't much, I don't know, I haven't seen rubidium around too much. Francium's radioactive, so there's very little of that. Cesium is the most reactive of all of the first row alkali metals. So would there be cesium hydride? Never seen it. I think I have cesium metal in my lab, in a sealed tube, in an explosion-proof cabinet. Because when it hits the air, it's pretty reactive. So that would be a source of H minus. So we could use a Grignard if we wanted to deprotonate an alcohol. Remember, when we were making Grignards, we had to keep alcohols away. But if you wanted to, you could use it. Certainly NH2 minus, if we go back to yesterday, right? The NH2 minus would react with the alcohol. It wouldn't do elimination, which is why we had to learn about putting chloride on, replacing OH with chloride. What else can I use? Well, if I look at the alkali metals, if you take sodium metal and you react it with water, what happens? Right, that's a classic general chemistry reaction. Yeah, it explodes and catches fire. But what do you get? You get Na plus with the OH minus, and then you also get the H2, which is why it explodes. So you're generating hydrogen gas. All it takes is a spark. The hydrogen and the oxygen then combust. I haven't seen any reports of a high school teacher doing this and wiping out the first row of students in a while. That tends to happen. That teacher then is fired, and the school district is usually sued for millions of dollars. So this is a reaction best done on YouTube. And there are plenty of them out there. I think the most creative one that I've seen in a while is somebody took the sodium metal and they pounded it into a sheet. They folded it up to make a little boat. They put it on the top of Hot Wheels tracks. Hot Wheels were quite the toy when I was a kid. That's the orange track that you can run the cars down. They put the orange track, they put it in a kiddie pool of water, and then they ran the sodium boat down the Hot Wheels track into the water, and it kind of floated there for a second and then exploded. That's the most creative I've seen. I've heard of other people doing other things that just we won't talk about. But sodium is pretty reactive. So is potassium. So we could use potassium to make our potassium hydroxide and H2. Potassium would be more reactive. And then, like I said, cesium. Cesium is the most reactive. My graduates, we don't have a graduate program anymore, but when we did, one of my graduate students, we were making a cesium alkoxide, which we'll make in a minute from this, in a dry box, meaning it's like a big box, like sometimes with gloves. It's sort of like a baby box with no baby in it. And then it's supposed to have no moisture in it, and he cracked open the cesium and put it in the round bottom, and it glowed bright red. And it wasn't my dry box, which is what you call it. So I was in back of somebody's office, and then he's like, and he said something, and I go, shut up, don't say anything. Right now it's drying out this dry box because it's reacting with any moisture that was in there, and there was a little bit of moisture in there. That's why it glowed red. It was that reactive. I think we've tried it with little baggies before since then and not used the box. So, tangent over, back to this. So how do I make an alkoxide? I replace the H2O with ROH. So I take my sodium and I react it with an alcohol, and what do I get? I get a sodium alkoxide and H2 gas. Is the reaction less reactive? Maybe. And I could do the same thing with potassium. The only reason I say, is it less reactive? It tends to be less reactive. But remember, alcohols are flammable, whereas water wasn't. So if you use something like methanol, if you react it with too much sodium, I'm not only going to be making hydrogen, I've got methanol that can burn, and that could be an even bigger disaster. But again, just substituting alcohol for water. So another way to make an alkoxide is to use sodium metal, or you could use potassium metal. So that's how we can make alkoxides. So you can make them by deprotonation, or you can make them by this reaction. In general chem, this is an oxidation reduction reaction. That's what it was classified as. So if we can make alkoxides, then we can do our Williamson ether synthesis, which is nothing more than an SN2 reaction with an alkyl halide to make the ether. So let's do one of those. Okay? So what do I use to make the alkoxide? I could use NH2 minus or H minus or Na or sodium metal. I can use any of those 4 reagents to make the alkoxide. Now, once I make the alkoxide, I can react it with a primary, secondary, or tertiary halide. So what would the products of each of those reactions be? Let's take the ethyl bromide plus the alkoxide. What would the product of that reaction be? You can write it on your little board. I want you to do the CH3CH2Br plus the cyclohexyl alcohol alkoxide. So what would be the product? This is going to be reaction A, this is going to be reaction B and C. We'll take them one at a time. So what's the reaction? What's the product of alkoxide plus A? I think you guys were okay. I think so. It's awfully small. Okay, I can see. Good, good. What? No. Okay, those are good. That's fine. Is there an O there? Okay. It's got to go inside. Okay. So if I was writing the mechanism for this, I would have the O minus attack the CH2 and kick off the bromine. Could we write the transition state for that? Because I could ask you to write the mechanism of that next week. So what kind of mechanism is this? This is SN2, and so the final product then would have the O attached to the CH2 attached to CH3. Okay. B. What would be the product now with isopropyl bromide? Okay. Okay. Isopropyl. Okay. Okay, Greg. One more. So this O minus comes down, kicks off the bromine, and we end up with our O and then our isopropyl group. So that would be the product. I just couldn't see the second line. Either because it's really small or it's not there at all. Okay. Okay, so then what kind of mechanism is that for B. SN2. So that's an SN2 reaction as well. Okay? Final product. Final reaction C. Okay, why are those two first reaction? Why are the first two reactions A and B SN2? Is the question. I don't know. Let's see, Cameron. So we've got a strong nucleophile plus a secondary halide. And in A, we've got a strong nucleophile plus a primary halide. So the reason that those are SN2 reactions is because we have to go back to our original chart that says strong nucleophile plus primary, strong nucleophile plus secondary is SN2. So then what's the product of C going to look like? Okay. I don't know yet. I'm waiting to see all the possible answers. What do we have? I've seen that. I've seen that. I've seen that. You want the tertiary butyl attached to the oxygen, I think. Anything else I've seen? I haven't seen the right answer yet. Why the double bonds? Out of curiosity. Okay. What's a tertiary butoxide? This is a tertiary butyl bromide. I mean, I will say the product has a double bond in it, but it's not either of those two double bonds. So when A and B react by SN2, it's because of the basic chart. Because I'm taking a strong nucleophile, reacting it with the primary and a secondary. What happens? What is this cyclohexyl alcohol alkoxide? It is not only a strong nucleophile, it is also a strong base. It is both a strong nucleophile and a strong base. So when it reacts with the tertiary alkyl halide, what does it try and do first? Well, first, being a strong nucleophile, it's going to try and do SN2 on the tertiary bromide. Except the tertiary bromide can't do SN2 because it's it's tertiary. So if it tries to do SN2, that's not going to work because this is a tertiary halide. So then what happens? It does E2. So what's the E2 product? Here's my alpha carbon with my leaving group, and then I have 3 beta carbons that are all the same. So then it's going to do E2. It's going to come in, grab that hydrogen, have that pair of electrons move like that, kick off the bromine, so that it will become an alcohol. In other words, it'll just deprotonate DH, and then the tertiary bromide will become that alkene. So this is another one of those examples where the this is another one of those examples where the strong nucleophile, when reacting with the tertiary, can't do SN2, so it turns around and does E2. And that happens when we have strong nucleophiles that are also strong bases. So, let's say I did this reaction. How many different products are there that I could form? Two? So again, tertiary alkyl halide plus the alkoxide. The alkoxide would love to do SN2. It can't because it's a tertiary. So it's going to do E2. What's the major product of that reaction going to be? So write that on your board. What's the major alkene product of this reaction going to be? Okay. It's double bond in the ring. Where's the double bond? On the second one. Okay. 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 So I saw both product A and product B there in terms of what you wrote. So which one do you think it's going to be? Is it going to be A or B? Or both 50-50? Why? Why do you think it's B? So you're thinking that this is a sterically hindered alkoxide. So if it is a sterically hindered alkoxide, that's going to give B, right? It's going to act like terse butoxide. I think a pretty strong argument could be made that that is sterically hindered. If it's not, if you don't consider it to be sterically hindered, then what are you going to get? You're going to get A, right? You're going to get the most substituted product. So it really boils down to, is that sterically hindered or not? I don't know. We'd have to do that reaction in order to try and figure out what the major product would be. But I would accept either one, because if you consider the tertiary, if you consider this cyclohexane alkoxide to be sterically hindered, you would get B, and if it's not, then you would get A. So I mean, you can make a case either way. So either A or B could be the major, depending on what you consider that to be. Is anybody bothered by that? We have to go do the reaction to figure out.
The trade contract, it looks like similar to that, but then obviously much bigger.
Right. Right, so there's a very strong case that it's sterically hindered. Why? Okay, that's the major product. You're correct. Somebody wants to say, well, I don't know, then they would write A and they're correct. Till we actually go do the reaction, which isn't happening today. We'll probably do it on the computer and figure out which one's the major product. Okay. So Williamson ether synthesis is make the alkoxide, do an SN2 reaction to make the ether. But there's a problem. If it's a tertiary alkyl halide, I have a problem. I can't do E2. Now let me end this discussion by restating something I said earlier. This was another example of a strong nucleophile, strong base, not being able to do SN2 and turning around and doing E2. The key phrase there is, this is another example. So what was our first example? What was our first example where if I tried to react this alkyl halide, it would not do SN2, it would do E2. So what other strong nucleophile, strong base have we had that did this? Well, what kinds of strong bases what kinds of strong base nucleophiles have we had recently? I know we have to go back, but we don't have to go back. Now, we never tried to do SN2 on a carbanion. With a carbanion like a Grignard carbanion, we never tried to do that. Exactly. We did try the alkynyl anion, and what did we say there? That if the alkynyl anion is reacting with primary or secondary, you did SN2. If not, what happens? We did an E2, and in this case we said the carbanion looked not very sterically hindered, so it would have given us the equivalent of an NH2 minus. So that's where we saw this before. So we do have this example of strong nucleophile trying to do E2. If it can't, it then is a strong base. It does E2. So alkoxides and alkynyl carbanions they have that characteristic. They'll either be SN2 or E2. And so that's why we've stayed away from them. Because usually what we end up doing is we end up using small alkoxides to do our Williamson ether synthesis. And the problem there is that small strong base is also a small strong nucleophile. So its tendency is then, with any of these, is primary or secondary, you're going to get SN2. Tertiary, you're going to get E2. And when we did not try and do SN2 with a Grignard. And that'll come back. We'll talk about that on. It's coming up. Probably next week. We'll come back to that and say, and I will remind you of this alkynyl anion, but I will also say, wouldn't it be a great reaction if we could take a Grignard and do an SN2 reaction, form a carbon-carbon bond? Because if you can make a carbon-carbon bond, that's the premium in organic, is making carbon-carbon bonds. You did that in the late 1800s, you won the Nobel Prize, and everybody knows your name for that reaction. The problem is Grignards don't do that. So we'll talk about the alternative to that next week. So that's Williamson ether synthesis. Now, I'm going to remind you of a couple things here. We could react a double bond with bromine and water to make the bromohydrin. We could then take that bromohydrin and react it with a hydroxide, which would come in and deprotonate the alcohol and form the alkoxide. Now that alkoxide could then, because when you make the bromohydrin, the Br and the OH are on opposite sides of the ring, this OH minus is in a perfect position to come in and do a backside attack on that carbon and kick off the bromine so that you could make then your epoxide. And so that was method 2 of making an epoxide. We started this morning by saying peroxy acid makes the epoxide in one step. Basically, what is this reaction? That reaction is nothing more than an intramolecular Williamson. And the molecule is perfectly set up with the O- to kick off the bromine. Now, can we do other intramolecular Williamson ether syntheses? And the answer is yes. And as the textbook says, these reactions turn out to be thousands of times faster than the intermolecular Williamson that we just did. Inter meaning two molecules, intra meaning one. So if I treated this molecule with hydride, what am I going to get? The hydride's going to do what? Deprotonate the OH. So I'm going to form that. Now what's that going to do? It's going to wrap around the molecule and come over here and kick off the bromine. So what kind of ring am I going to make? How big is it going to be? What? Square? 4? 5? What? Did you say 6? 6? So what's it going to make? 4, 5, or 6 membered ring? I know, you just said 5, now you're saying 4. So here's what... The oxygen is going to be part of the ring. The oxygen is going to be part of the ring. So 6? Right. We can probably resolve this issue by doing one simple thing. 1, 2, 3, and 4, and then 5. So my O is going to attach to carbon 4. Let's count up the sides of the ring. So here is 1, 2, 3, 4, and then the O attached to 4 is going to be 5. So I'm going to form a 5-membered ring with the oxygen on the inside of that ring. Okay, what's the oxygen attached to? Number 1 and number 4. Right? It's already attached to number 1 and it's going to form the bond to number 4. So then I've got 1, 2, and 3. 5 is attached to... No, 5 is attached to carbon 4. Really? I mean, 5 is attached to 4. So over here, I need a 5. Right, I didn't draw it yet. I didn't go anywhere, I just didn't draw it yet. That's everything, right? So I got a 5-membered ring. With the oxygen attached to carbon 1, it's forming a new bond to 4, and then 5 is also attached to 4. On the what? Because what's happening is just like this oxygen up here is reacting with the carbon and becoming part of the ring. This one down here is doing the same thing. It's reacting with 4 to kick off the bromine, so there's going to be a bond formed between oxygen and carbon 4. So if this was another molecule, like if 1 and 2, or if 2 and 3 weren't bonded together, the O- would come in, kick off the bromine, and still be attached to carbon 4. But now what's happening is now it's forming a ring with the other carbons it's attached to. Okay. So what I find, because when you're throwing out numbers, I just drew a problem. I didn't know what the final ring was going to be. So as you're throwing numbers out at me, I'm not going, oh, they're right, nope, they're wrong, because I didn't bother to try and figure it out, because that's how you figure it out. Number the carbons, and then figure out how they're attached. Okay? So this is an intramolecular Williamson ether synthesis. And this is a way to make a cyclic ether. This is intramolecular, sorry. This is intramolecular. The one on top is also intramolecular. And what we did on the previous slides is intermolecular, right? They're intra for both because they're happening within one molecule, right? Intra means within the same molecule. The easiest way to remember that is sports, right? If you're doing intramural, then what's happening? It's intramurals. And if you're traveling, it's intercollegiate, right? Right. Maybe there's another way to remember it better. So if you write the numbers down, that helps you figure out what the ring size would be. And if there's other stuff attached, where the other stuff should go. Okay. All right, so let's take a break. And when we come back, I want to do that reaction. I want to make that ether. We already know what I cannot use, right? What can I not use? I cannot use no, that's well. You're right. Yes, I cannot use anything that would want to go by SN2 because it can't go by SN2. So what did we just try? What did we just do? What would we use here to try and do that? CH3, CH2, O. Minus. So I cannot use that, right? Right? Can't do that. Do we agree or disagree? Why? Thank you. If I try and do that, it's going to do E2. So I can't do that. Anybody have an idea, though, how I could make it work? Because I do. What? I like that idea. Let's use a weak. So what's the weak nucleophile I'd want to use? Well, but this is what I want to make. I want to put that part onto the terse butyl. So right idea, water is a weak nucleophile, but that's not the specific one I want. I want a CH3, CH2, O, H. So if I react those two together, will I make that ether? Yes, no? It's going to do SN1, not SN2. Well, let's think about that. So, if I do this by SN1, this is going to take us back, oh God, 3 weeks. Normally I would say this would take us back to last semester, and then no one would remember. But it's only been a couple weeks. So if I do this by SN1, what's the first step of my mechanism? What leaves? The bromine leaves. So I don't need to take anything, I don't need to have anything, because this is a tertiary. So that's going to do what? And a Br minus. Okay, what happens next? So I'm going to take my alcohol, which is my weak nucleophile, react it with the carbocation. And I'm going to make my oxonium ion. And then what's going to happen? I'm going to lose my H plus to give me my final product. So that, as an SN1 reaction, would work perfectly fine. It's an SN1 reaction. It would also be called, since I'd use a lot of ethanol as the solvent, it would be called my solvent is my nucleophile. I'm cleaving my solvent, OH bond. Solvolysis. Solvolysis. So another way to make ethers is to react a secondary or tertiary halide with an alcohol. Because secondary, tertiary halides can undergo SN1. Once you lose the halogen, you're going to have a carbocation, and your alcohol is going to come in and react, and you're going to make your ether. So I don't need SN2 for that reaction. I can just do it by SN1. Okay. Now that reaction looks pretty small because last semester we were incorporating all the transition states when you had to write that mechanism. So it's going to be a little bit easier without transition states. So that's another way to make an ether. But it's got to be a secondary or a tertiary halide because it has to go by SN1. All right, what about a third method to make ethers? I want to react tertiary butyl alcohol and methanol together, and I would like to make tertiary butyl methyl ether. What do I need to do this reaction? I'm going to do this like a solvolysis, maybe. No. Protonate the OH group, turn it into water, and have it leave. Great. So what do I need? So I need H+. Now, I need one more detail. Where did DH+ come from? HCl? Cl, yes or no? What? I hear a no. It's not a very confident no. So if I used HCl, what would react? The Cl would react with the carbocation once. So if this H plus comes from HCl, my H plus is going to protonate my alcohol, my water is going to leave, and then my chloride is going to come in and attack my carbocation. Is that what I want? No. So I probably shouldn't use HCl. So what's my other choice? Water's not H plus. What? H2SO4? Good question. Because that's what we used for it. That's what we used. That's maybe. No, that's a good point. And it was kind of the point that I was hoping you would make. It's like, okay, we want H plus, but we don't want a nucleophile to go with it. So what do we use? H2SO4. But we don't want this to do elimination. So what should I avoid? Heat. So if I don't heat it, it won't undergo elimination. So if I just use H2SO4 and no heat, it's just going to act as an H plus source. H3PO4, no heat. Without something that doesn't have a conjugate base that's a strong nucleophile. Or that's even a nucleophile at all. Okay, so, I mean, there is a method. It may seem like I have no point. I always have a point. Sometimes I know what it is, sometimes I don't, but there's always a point. So why are we using the H plus? We got to use an H plus with no nucleophile, H2SO4. All right, great. So which OH do you want to protonate? Could do both, but your choice. The H plus could react with either one of those OHs. I'm asking you, which one do you want to react it with? The tertiary one? I don't know. Let's find out. So let's react the tertiary one with the H plus. So what am I going to get? I'm going to get an oxonium ion. Maybe we need the wheel. This is relatively easy, not emotionally shattering stuff. This will not cause your self-esteem to be destroyed. Maybe. So Greg, what do we do next? That would be the final step if I was adding the water. Now I want to get rid of the water, so what should happen? Somebody help Greg. Cameron. Okay, so the water's going to leave. We're going to break the OC bond. I'm going to form the carbocation and then the neutral water molecule. Okay, so this is going to be the first step in what we would do with dehydration. Or if we were adding HCl, we would do this. Okay? So next step. Remember, our goal is to make an ether.
Max.
Okay, so I'm going to add the methanol to the carbocation, and I'm going to make the oxonium ion. And then what's the final step? Lose the H plus. You lose an H plus off of the oxonium ion, so that now I would form my ether. How would I classify this reaction? Is this a 1 or a 2? 1, because there's a carbocation intermediate. So this would be classified as an SN1 mechanism. Okay, so I can make an ether from 2 alcohols. There's a complication to it, which I'll come back and talk about. So, let me... There it is. Well, let's talk. Let me talk about the complication to this. Here's the complication. Every one of these steps is an equilibrium step. Every one of those steps has an equilibrium. So that means the overall reaction, I'm going to be making the ether in equilibrium. Right? The overall reaction would be up here. You would have 2 alcohols reacting to make the ether, and H plus is truly the catalyst because it's used and then generated in the final step. So how am I going to push this equilibrium to the right? Le Chatelier's principle is going to be of limited value here, because what I'd like to do is I'd like to basically make the ether in 100% yield. So here's what we do. This is how you make ethers industrially. What you do is you say, which molecules have the higher boiling point? Alcohols or ethers? Which one has a higher boiling point? Alcohol or ether? If nothing else, take a guess. Has the higher boiling point? Guess again. The alcohol has the higher boiling point than the ether. Well, that's a good question. Why? It has to do with intermolecular forces. Which one has a higher intermolecular force? Alcohols or ethers? alcohols because they hydrogen bond. So an ether has a low boiling point. We've all taken lab, right? We've all taken organic lab. You may not be taking it this semester, but you've taken organic lab, one lab, unless you're in some sort of program where you don't have to take organic lab. So what kind of worthwhile program is that? Right? What do we use ether for? Extractions. Why I'm going and breaking down the third wall here, or the fourth wall, or the fifth wall, right, by talking about lab and lecture. But why do we use ether as an extraction solvent? Number one, it doesn't dissolve in water. So I can pull your organic stuff out of the water. Number two, I extract, I dry, and I evaporate. Like rotary evaporate, if you have those at your school. So, why is ether a good extraction solvent? Because it doesn't take much energy to evaporate it. Right? I don't need to have boiling water to evaporate the ether. Now, if I'm using a rotary evaporator, I don't even need to have hot water. So, back to the point. How do I push this equilibrium? How do they do this industrially? What they do is they set the temperature just hot enough so that when the ether gets formed, it boils. And then it goes up into a condenser and gets collected and removed from the product. So now Le Chatelier comes into play because now I'm constantly removing product and I can pump in more of the alcohol because the acid catalyst is nothing's going to happen to it. So if I want to continuously make ether, I'm going to set the temperature just hot enough to get the ether to boil off when it's done. And then the alcohol stays and reacts and I continuously make ether. We're not going to a really high temperature so that we're not going to do any dehydrations. Because like diethyl ether boils at 35, right? I don't know, you had to write it in your notebook just a few weeks ago. I know. I mean, if you have a lecture professor who knows nothing about what's going on in lab, they're not going to ask you these questions, but I do. So, I mean, 35 degrees is not probably warm enough to cause dehydration. T-butyl methyl ether. And this, by the way, is your additive in gasoline besides methanol or ethanol. So this is an oxygenate that's added to make your gasoline burn a little bit cleaner. We don't use it in lab because it has an annoying smell. And there's probably more environmentally friendly things we can use. And this is the contaminant that ends up in the ground, in the soil outside of dilapidated gas stations, so that they have to go in and they have to dredge up all the soil because it's contaminated with gasoline and TBME, tertiary methyl ether. So it has issues, but it's one of the oxygenates that's used. So that's how we can overcome this equilibrium, is by taking advantage of the intermolecular forces. Okay, so you wanted to protonate the OH on the T-butyl group first. Does it matter? Let's find out. Let's protonate the OH on the methyl for the methanol. What are we going to form? We're going to form an oxonium ion. What happens next? I mean, it could if you wanted to go backwards. I'd like to go forwards to make an ether. What? Would the other thing become, what other thing? The tertiary alcohol thing? So you want this to be the nucleophile? Well, you can't ask you can't answer my question with a question. I'm the only one that's allowed to do that. So is that what you want to do? Do you want to lose the water?
Yeah.
So do we want to lose water? No. Because if we lose water, what do we get? We get a CH3 plus. Is that stable? That's worse than a primary carbocation. So we can't lose water. So how about we take this as a nucleophile, come in, and have it do that? And then lose the H plus. What kind of mechanism is that? SN2? We agree it's SN2? Why is it a 2 mechanism? Because there are no carbocations. So that's a 2 mechanism. Is it legit? Is that a legitimate mechanism? I mean, I don't see anything wrong with it. I mean, is it going to occur as quickly as the other one? Probably not. But could it happen? What? I mean, it could happen. What? Yeah, I mean, the tertiary, it's a sterically hindered nucleophile, right? I mean, this is a sterically hindered nucleophile, but our saving grace here is that this methyl group has no hindrance at all. So, I mean, if that was an ethyl or an isopropyl, then no, that's not happening. Well, in this case, it doesn't matter that this nucleophile is tertiary as long as that's methyl. If it got bigger than a methyl, we might have an issue. But remember, we have the other pathway too. So which of these two pathways is going to predominate? Probably the one that we wrote first, the carbocation. But is this a possible mechanism? Yes, it is. So, we can make ethers from alcohols. Is it going to be an SN1 or an SN2 mechanism? I don't know. It's going to depend on the molecule. It's going to depend on the pathway you want to go. So, I mean, if it's 2 tertiaries, it's going to be a 1 mechanism. If it's 2 primaries, it's going to be a 2 mechanism. If it's primary and a secondary or primary and a tertiary, it could go either way. So that's how we can make ethers. Another way. There's lots of ways to make ethers. There are only a couple of reactions of ethers. What can I do with an ether? Well, there's very few reactions because ethers don't tend to react, which makes them great solvents. You want a solvent for a Grignard reaction? Ether is a great solvent. Can't be deprotonated, pretty much inert, except a couple reactions. Number 1, ether, oxygen, flame, makes CO2 and water. That is what kind of reaction? Combustion. That's a combustion reaction. When we're using ether in the lab, no Bunsen burners. The hot plates, questionable. If you're going to heat something, you always want to heat it in a water bath on the hot plate, because if a drop of ether, when you're heating it, flies up in the air and hits the top of the hot plate, you could get a little bit of a flame, and then that flame goes back into your round bottom or your Erlenmeyer flask, and then the next thing you know, the hood's on fire. Not really. No, it wasn't the time that I saw it and had to get the fire extinguisher. No, it was not very fun. So when we're using ether or ethanol, we always heat that in a hot water bath. Okay. Ether also has another annoying feature, and it's that it's heavier than air. So in our old building, before we had hoods for everybody here, and if you're in an organic lab without hoods for everybody, God help you. But we used to use ether, but then the problem was that if somebody down at that end of the bench was using ether, the vapors could actually travel all the way down the bench to here, so that literally you could light the fumes on fire and the flame would shoot back to their container. So you had to be careful of that. Right? And it makes a whoosh sound when it happens. It is, again, until you have to break out the fire extinguisher. In graduate school, the Belgian graduate student decided that he was going to recrystallize something on a hot plate with no hot water bath. And then he tipped it over, and then the next thing you know, you hear that whooshing sound, and you look over at the wall, because I can't see the hood. I look over at the wall, and there's a nice flickering orange color. And then I hear him, "If you know where the fire extinguisher is, get it." Because he had backed up, and he was like basically backed up against the fire extinguisher. So I'm like, we'll get the fire extinguisher. Kid from across the hall came over. We put it out. We handed him 2 fire extinguishers and said, "Good luck with the paperwork on that." There was some ethical issues of cover-up where he went and got everything. He goes, "Look, it's perfect." And I said, "It wasn't like that. He caught it on fire." So that's why we're pretty particular about ether. There's one more issue with ether. as well. Yes.
So, if you have like oxygen, like,
No, it would just contain the fire. When we tell you here, if you have a fire or anything, when you have a fire, close the hood sash and yell. It's not because the hood sash is going to put the fire out. It's just going to contain it. Even if whatever was to explode, the glass on the front of the hood can take an impact. I mean, it can take a pretty good impact and not crack. Or if it does crack, it's like your car windshield; it just cracks. So it's a very high safety glass. And we've had waste bottles explode and not break the glass. I don't think we've had a fire. So, but we've had fires and then you just kind of blow them out. If somebody doesn't put their condenser on top of their round bottom very well, and there's a gap, then sometimes it creates a fire. So, but ether, you got to be careful with ether because it's very flammable, right? It was one of the earliest used anesthesia agents, but you had to be careful of it because it was flammable. So, reaction number 1. Reaction number 2. Over time, ether will react with oxygen gas. Oxygen gas has a radical portion. The oxygen can be a diradical. So you can have a free radical reaction occur here. What happens is that the carbon next to the oxygen can actually remove that hydrogen and have the other unpaired electron go to the carbon, so that you end up forming this species. And then the oxygen now has a hydrogen bonded to one end. It turns around and it couples together with now your carbon radical, and it forms a peroxide. Ethers have a tendency to form peroxides over the course of their lifetime if they're not handled properly. In other words, you fail to keep oxygen out, which is impossible to do. The danger of a peroxide is that the general rules of making explosives, and do I really need to say this is in theory, not in practice? I feel like I need to say that. But if you want to make an explosive, you embed a gas molecule into your molecule. So if you embed an oxygen gas molecule and you make a solid, if that decomposes, your solid goes to a gas, and so there's a tremendous volume increase. And if there's heat, then gas laws say there should be even more of a volume increase, so that if you have an ether bottle and you see any white solid at the bottom of it, you'll walk out of the lab, because that peroxide is basically explosive. It can detonate by shock, meaning you go to pick the bottle up, or it can also explode by heat. How explosive? Well, like I would pick it up with a hand I don't write with. So that way, if it explodes, I can still write. That's the general rule of picking up things that could explode. You always use the hand you don't write with. I'm not joking. That's a rule. How bad could that be? I have seen people come in spacesuits to take old ether bottles out of the lab across the parking lot to the bomb squad place, like the vehicle, in case it explodes. Silver suits. It was pretty impressive. Because there used to be ether bottles that people would just find because they'd be in the lab so long. And glass doesn't help. That's why our ether bottles are all like in metal, because that helps prevent the peroxide formation. So if you heat this, the guy across the hall from me in graduate school, he was rotary evaporating an ether. It had a peroxide in it. It exploded the round bottom, and the piece of glass hit him right in the safety glasses and took a chip out of the safety glasses. I mean, needless to say, what it would have done to his eye had it hit it. But he had safety glasses that weren't goggles, but real safety glasses. So ethers we have to be careful with. We have to make sure there's no peroxides in them, because they will explode. Old bottles, very bad. Same thing. That's what we use most of the time. However, I did get a call one time from a former research student when he started teaching. I think he was teaching at Riverside. And he's moved on. He's principal of Mentor for a while. Now he's like the superintendent of next to Mentor. When I saw students at science fair that went to Mentor High School, I would ask if he was still there, and then I'd tell them if they ever got in trouble, they could use my name as say that I told him he should take it easy on them because I know what he did as a college student. But he gives me a call and he says, we have diisopropyl ether in the lab. And I said, where are you calling me from? And he's like, the lab. And I said, well, you should go out in the hallway and shut the door very carefully. Because the problem with diisopropyl ether is, now what kind of radical do I form? I'm actually going to form a secondary radical, which is a lot more stable than a primary one with diethyl ether. So I'm like, I'm sure there's peroxides in there. I think you need to call somebody to come and get it. Because that's going to definitely have it, because it was very stable. And of course he didn't. One of his colleagues said, I'll take care of it. And he grabbed the bottle with whatever hand he grabbed it with. And fortunately for him, nothing happened. But that person's an idiot. Because it could have exploded in his face. So that's two reactions of ethers. And neither one of them is helpful. Right? So we'll talk quickly about the third one. Tomorrow we are going to do free radical halogenation. So that's what the reading assignment or the video is for. That's what that is for tomorrow. I hope I'm not getting a sense here that no one's reading or watching the videos. But tomorrow's topic is all going to be free radical halogenation, because that's kind of a difficult topic to talk about. So if it doesn't make sense, come in and say, it doesn't make sense. But kind of be specific if you can.